And there are also other things reported in literature to manipulate the membrane. You can use special dendrimers, carbon nanotubes, or fusogenic liposomes that feature especially POPE as a phospholipid. You have the porin-mediated uptake. Here we have, first of all, the general porins. These are the main entrance route for the enterobacteriaceae, like Escherichia coli or Klebsiella pneumoniae and Salmonella enterica. So these pores allow for the passage of small hydrophilic substrates. They can also allow for, or it is advantageous, although these pores are called general and unspecific porins. We have some negatively charged amino acids, but also negatively charged molecules and neutral substances can pass. So that it prefers positive charges does not mean that you don't have any chance with negative or neutral substances. The only thing is that you must probably choose the molecular weight or the molecular size a bit lower. The lower you go with the molecular size, the more degrees of freedom you have. In general, we have these general porins also in Pseudomonas and Acinetobacter, but that also doesn't mean that we have a significant passage of antibiotics here. We see, that looks nice, 3000 Dalton as a molecular weight cutoff, but the porin, for some reason, does not allow a very fast passage of the antibiotic. So I suggest, or I suppose that aiming for a general porin-mediated passage of antibiotics in Pseudomonas is not really a favorable strategy. On the other hand, also we see these molecular weight cutoffs, for example, for E. coli, that is between 600 and 700. Usually 600 is considered as a limit, but you can exceed this a bit by following certain strategies. Here we have a compound reported by Rugiu et al., where they allowed these molecules to have a certain conformation that makes them fold together. So although the molecular weight is quite high, it is still small enough to go through these porins. And again, we have here also a positive charge. Okay, let's go to the specific porins. They can be subdivided. Some are ligand-gated channels. That means they open only in the presence of the substrate. These specific channels give the bacterium the chance to get nutrients that are not so highly concentrated in its environment. So even at low concentrations, you have a quite good transport compared to non-specific pores. They have a special binding site for these for the respective compounds, and these pores are usually used for certain carbohydrates, amino acids, fatty acids, and nucleosides. I would like to question if this route is also a favorable route to deliver antibiotics, because these specific channels are really very specific. One example is here this TSX channel of E. coli, which just allows the passage of nucleosides. No nucleotides and also not nucleobases can go through. So regarding the uptake, you have these TonB-dependent transporters. Yeah, these also are composed of an entity in the outer membrane, in the periplasmic space, and then one in the inner membrane. And what you see is that it allows also for quite large substances to be taken up. Even vitamin B12 is taken up through this pathway, and this has a molecular weight of 1,355 Dalton. It is mainly known to take up iron complexes, but also recently it was shown that other compounds are taken up. Yeah, other metal ion complexes, but also sugars and vitamins. And we have already a FDA approved representative as an antibiotic, yeah, that gets taken up through this pathway. It's cefiderocol. You see it has this catechol group, yeah, that allows to complexate iron. And yeah, this I think has the chance to become a popular pathway to yeah, so that drug developers can also use this pathway for rather large compounds to be taken up. The big problem here is, though, that for bacteria it is quite easy to just downregulate these transporters or to modify the binding site, and then you have resistance formation again. So regarding the distribution, there hasn't been done much research yet, but one very popular or very well-known case is the case of the aminoglycosides, where we see that they are inactive in anaerobic bacteria. Those do not generate this proton motive force caused by the respiratory chain. I try to indicate this here by the plus symbols in the periplasm and the negative symbols in the cytoplasm. Aminoglycosides depend on this to cross the inner membrane, and if it's not there, it doesn't work. Yeah, it doesn't matter how much gets through the outer membrane if the aminoglycosides cannot get to the ribosomes, which are in the cytoplasm. And in contrast to that, we have compounds just like tetracycline or ciprofloxacin that are zwitter ions and are also active in anaerobic bacteria. They have a certain fraction that is uncharged, so they can permeate much easier through this phospholipid bilayer than this multiple positive charged aminoglycoside. So, and also, yeah, the metabolism is quite important to consider, and this is not just an issue for the beta-lactams. In principle, yeah, also lactone or ester groups, they are, I think, in many fields known that they can undergo hydrolysis, and you must also be aware that primary and secondary amines undergo acetylation, AMP conjugation, phosphorylation. This has been reported already in literature. Hydroxy groups can also get acetylated by enzymes. Polycycles like tetracyclines can undergo oxidation, and there are probably many more mechanisms which we don't know yet. And the clinical relevance and the quantification of this degradation is very well understood yet. So we need also investigations on that. One interesting example for an enzymatic degradation among compounds that are just emerging, this is from our institute, are, for example, enzymatic modifications of so-called quorum sensing inhibitors. Here, this compound was designed to inhibit an enzyme in Pseudomonas aeruginosa, PQSR. And it turned out that an enzyme exists that just converts it to an agonist. Yeah, and it's really important to pay attention to this. So, and regarding the Efflux, we have these R&D, these Efflux compounds of the R&D superfamily, which are most important in gram-negative bacteria. They get their power from the proton motive force. So in theory, if you inhibit the formation of this proton motive force along the inner membrane, you can also deactivate those pumps. General rules. You can say that with increasing lipophilicity, with increasing molecular weight, and with decreasing charge, you enhance the efflux. And there have been also studies done on E. coli and Pseudomonas to find out specific rules. It's of course not standardized. Every group had their own strategy how to tackle this question, what is prone to efflux and what not. But also here in general, you can say don't make the compound too lipophilic and don't make the compound too flat and too flat. Regarding the size, there is a later graph. It is not necessarily bad to make a compound small. That might be a bit counterintuitive, because you also would imagine it like a pore, and it would go through much easier the smaller the compound is. But the things are not the way they seem here. And there's, of course, more research necessary to find further physicochemical properties that rule the efflux. Many of you know probably the research by Michel Richter and Paul Hergenrother. They found these so-called entry rules. You must, or it is recommended to have a nitrogen, preferably a primary one, the three-dimensionality, so the bulkiness of a molecule should be actually low, it should be rather flat, and the molecule should be rather rigid, so it should not contain too many rotatable bonds. Regarding the nitrogen, based on what we've heard before, it makes sense. We have a better uptake through unspecific porins because of this constriction region with the negatively charged amino acids. You have a better chance for the molecule to pass. If you have more than one nitrogen, you might also allow for self-promoted uptake, which I mean by the displacement of divalent cations from the outer membrane. This might be even effective for compounds that are a bit larger than 600, 700 Dalton. And also, if you increase the charge by introducing nitrogens, you also decrease the efflux. The low globularity makes also sense. It allows for better diffusion across the lipid layer, and also, as said, the molecules should be rather flat. You have less efflux. Also, the low number of rotatable bonds, which goes a bit in line with the globularity. Of course, if the bonds are not rotatable, they are unsaturated and rather flat. But you also then have a better diffusion across the lipid layer, but also a better passage to the unspecific porins. In many cases, I've seen that that certain functional groups, for example, in ciprofloxacin, the carboxylic acid group, and the secondary amine group, need to have a certain distance and a defined distance to get well through the porins. And there was also this other group that by Heinz Moser, who investigated the average physicochemical properties of antibiotics that are active against gram-negative bacteria, and they compared it also to those compounds that are active against gram-positive bacteria and those that are just commonly used against various diseases in human beings. And they also found out that the molecular weight compared to gram-positives is quite low. The hydrophilicity is in general lower than for the other two groups, and also the amphiphilicity. And yeah, all this you also find when you look at substances that have been already released to the market. They are all rather small, they are all rather hydrophilic, and yeah, they are also zwitterionic partially, but also have some positive charges. I would relativate also a bit the use of the entry rules. It also depends a lot on the compound. You have here 6 compounds that are quite, you can say, rather promising candidates, more or less advanced in drug development. But you see that these compounds have all, for example, only 2 out of these 6 compounds have an ionizable amine. But what is again in line with the entry rules is that they are all rather flat. They are quite rigid and have a low molecular weight. And the log D is not in the negative range, but only slightly above. One exception is here this compound G0775, which is much more flexible, 16 rotatable bonds, and the compound is of course also quite large with a molecular weight of around 900 Dalton, and is also more lipophilic. Let's say the compound can afford to do so because it has these multiple positive charges. This again allows for the self-promoted uptake. Can probably again perturb the LPS layer of the outer membrane and then enables for its own enhanced uptake. So, and regarding the molecular weight, I say 600 Dalton, or it's in my field, 600 Dalton is considered as a molecular weight that should not be exceeded. There is, I think, when you compare different studies, some kind of 2 maxima. You can either aim for decreasing the molecular size, but maybe it's also, I think often it's important to not make the molecule too small. The larger the molecule is, the more functional groups you could introduce to also cause some interactions with the target site, and this needs to be balanced. So if making the molecule smaller is no option, maybe it's okay to keep the molecule at around 600 Dalton, because what we see here is when we compare the molecular weight cutoff of the porins to the efflux efficiency, that it drops at around 600 Dalton again. 550 to 600 Dalton, these compounds do not get so much efflux anymore. So you have a little maximum of bioavailability maybe here. Which could be a possible strategy to aim not for a compound then that is somehow between 450 and 550, but make it even a bit larger and make it a bit more compact, but keep it at this molecular weight. So, but it gets, of course, even more complex. We have these different rules. We have found out, molecules should be small. They should have low number of rotatable bonds. Should be rather flat and should have an ionizable amine. But this leads to a conflict with the toxicity, because probably these compounds will then also very well go into the mammalian cell and also might bind very unspecifically to internal receptors. So yeah, it should be wisely chosen whether to introduce an ionizable amine or not, or how many ionizable amines one should introduce. The more I introduce, the more I will enhance the cytotoxicity of this compound. So I think it is a rather good strategy to increase the selectivity of these compounds by making it more hydrophilic, introducing only a few charges, and yeah, if possible, make them zwitterions even. Yeah, or if all this fails, you of course have then, for example, the Department of Drug Delivery, which can think about certain formulation technologies. I mentioned the fusogenic liposomes that yeah, could enhance the drug uptake. So to conclude, the optimal bioavailability of drugs is very dependent on yeah, on numerous factors. It depends on the outer membrane proteins that are there. It depends on the enzymes that are there. So in the end, it depends on the species, on the strain, on the fact if the bacterium is already resistant or not, and what kind of resistance this is. Yeah, and this also determines, of course, it also depends on if these bacteria are cultured in an aerobic or anaerobic environment. And yeah, of course, the molecular structure is very important. But yeah, I cannot, in this case, give you some holy grail rules that will allow for the uptake in all bacteria. And I think also in general, it is more recommended to see the different factors, yeah, distribution, efflux, uptake, and enzymatic degradation as an interplay, and it would be probably more useful to make a computational model that can predict the efflux and all the other parts of the bacterial bioavailability, and then you can check based on the simulation, okay, what is the problem the compound has at the moment? Is it the efflux? Is it the enzymatic degradation? Or is it the uptake? Something like this. But as some general rules, yeah, you can say the smaller the better. Log D should be yeah, below 0 ideally. A positive charge or zwitterions are favorable. Zwitterions, I think, are favorable to that extent that they have, yeah, that they are likely to also have an uncharged fraction, which still allows for some degree of passive permeation. So they are not too porin-dependent. So, and yeah, if you play a bit around with the charges, yeah, maybe 2 ionizable amines or 3, this might still make it happen that the compound gets taken up not only through the porins but through self-promoted uptake. So again, porin independent, and this will also make these compounds possibly active against yeah, these tougher bacteria such as Pseudomonas aeruginosa or Acinetobacter baumannii. And yeah, there are these other features. Yeah, I mentioned the neighboring amines, but you can think of an iron chelator to enhance the uptake through active, yeah, active uptake pathways. And in the end, yeah, it should be also further explored to yeah, co-apply membrane permeabilizers or efflux inhibitors. Enzyme inhibitors are already on the market, but it is also worth doing more research on compounds that block the proton motive force, for example. I mentioned the polymyxin B that enhances the permeability of the membrane and then allows for a better uptake of other compounds too. So as a very last step, I also, because it's Biosolve IT, I also want to introduce you to a couple of models which are currently used, and I want to focus a bit more on the computational models. We see, there are a lot of models out, and it is not, these are mainly wet lab models. You can test the uptake of compounds in living bacteria. That is not very, this is not very high throughput, and you don't know really what the underlying mechanisms are for a good bioavailability or a bad bioavailability. These other mechanisms rather mimic the uptake, and preferably the porin-mediated uptake. What I notice is that there are not many assays out that allow for the permeation, that allow for the prediction of efflux or for the enzymatic degradation. So there's still research needed. And maybe this can not only be done in the wet lab. For example, this is subject of past research, but also ongoing research so far. Mostly the phospholipid membranes and porins have been investigated using molecular dynamics. But in future, I know there are also groups already involved in the molecular dynamic simulations of efflux pumps. Molecular dynamics is or are a powerful tool to check for membrane disturbance, the membrane affinity of compounds, to also see where in the membrane the actual barrier lies. Is it the phospholipids, if you look at the phospholipid bilayer, or is it the phospholipid, is it the acyl chain, or is it the phospholipid head groups, or in the porins? Maybe there is some kind of constriction region that blocks the compounds to go any further, but also they can tell you what is actually the permeation mechanism. What kind of orientation does this compound have to go through? But this is, it's not that trivial. You need to select the right, what I call now physics engine, the right force field. The physics have to work in this simulation appropriately, and it requires a lot of computational power. And machine learning is also a topic that becomes more important in the development of new antibiotics. And here is just an overview of machine learning techniques that have been already employed in the literature or by companies. Also, in one of my papers, I used the random forest analysis, which was quite advantageous because you can do such a analysis already with a relatively low set of compounds, and you can also conduct such a random forest analysis, although maybe one or two data points are missing, so the data set doesn't have to be complete. This deep artificial neural networks haven't been really employed yet to determine antibiotic or the bacterial bioavailability. They just screened, they just trained a network with a lot of MIC values and found out such a compound that could be maybe repurposed in future as an antibiotic against gram-negative bacteria. And I mentioned here before the naive Bayes machine learning method that is employed by the Spark platform, but I have to disappoint you a bit. They changed the platform. They changed, or they provided all their data now to the CDD vault, and it's publicly available. If you need drug accumulation data, if you need activity data of various compounds, it's perfect. You can look at various structures and look at the MIC value, physicochemical properties. But the machine learning part apparently went missing there. This is a bit sad, but maybe will be reintroduced. Who knows? And with this, I've come to the end of my webinar. And yeah, I want to thank, of course, my boss, Professor Klaus Michael Lehr, and my colleagues, Professor Anna Hirsch, Professor Olga Kalinina, who is the IT specialist in our department, and also Henny, my former colleague here at TIPS, and also Carla, who does also some molecular dynamic simulations across phospholipid bilayers so far in our department, and my master student Mohammed, who is also very passionate about the finding rules or improving the permeation across gram-negative membranes. Thank you very much for your attention.